MEG 224, Engineering Mechanics 2, Dynamics, Lecture 7, Part B, Planar Kinetics of a rigid body, force, mass, and acceleration. This can be found in Engineering Mechanics Dynamics by R.C. Hibella. Lecture objective. The objective of this lecture is to develop the planar kinetic equations of motion for a symmetric rigid body. Planar kinetic equations of motion. This study will be limited to planar kinetics to rigid bodies, which along with their loadings are considered to be symmetrical with respect to a fixed reference plane. Since the motion of the body can be viewed within the reference plane, all the forces and couple moments acting on the body can then be projected onto the plane. An example of an arbitrary body is of this type shown in figure A. Here we have different forces acting on the body, and the body is in inertial reference frame, X and Y, and this mass center is at G with the weight acting at the mass center, and we have moments as well. This object is subjected to angular acceleration alpha and angular velocity omega. Here, the inertial frame of reference X, Y, and Z plane has its origin coincident with the arbitrary point P in the body. By definition, these axes do not rotate and are either fixed or translate with constant velocity. Equation of translational motion. The external forces acting on the body in figure A represent the effect of gravitational, electrical, magnetic, or contact forces between adjacent bodies. These are forces that are acting externally on the object. So this force system has been considered previously in the analysis of a system of particles. The resulting equation can be used here, in which case summation F is equal to MAG. That is, this equation referred to as the translational equation of motion for the mass center of the rigid body. It states that the sum of all the external forces, summation F, acting on the body is equal to the body's mass times the acceleration of its mass center, MAG. For motion of the body in the XY plane, the translational equation of motion may be written in the form of two independent scalar equations, namely, summation Fx is equal to MAG in the X direction, and then summation Fy is MAGY in the Y direction. So equation of rotational motion. Let's now determine the effects caused by the moments of the external forces system computed about an axis perpendicular to the plane of motion. That is, the axis is the Z direction and passing through the point P. Z is perpendicular to this now. This is X, this is Y. Then, as shown in the body, in the free body diagram of the ith particle in figure B, Fi, this is capital Fi, represents the resultant external force acting on the particle. And small fi, this represents the resultant of the internal forces caused by interactions with other adjacent particles. So if the particle has a mass mi and its acceleration is ai, then its kinetic diagram is shown here in figure C. So the resultant force F is MIAI. So summing moments about point P, this P, will require that the moment arm times the force. So R cross Fi, then plus R cross F small I, because the resultant moment, force, the resultant force here is the vectoral summation of Fi plus Fi, which is Fi plus Fi. Therefore, the moment is force times perpendicular distance. So summation of all the moments of the moment acting on I particle is R cross MAIA. So that's the force. Therefore, the moment about P can also be expressed in terms of the acceleration of point P. This is point P. That's the acceleration. So if the body has an angular acceleration A and the angular velocity omega, as from the previous lecture, we have that AB is equal to A plus alpha R of B with respect to A minus omega square R of B with respect to A. So where AB is the acceleration of the point B, and the A is the acceleration of the point base A, as in that equation, alpha is angular acceleration of the body, omega is angular velocity of the body, and R of B with respect to A is position vector directed from A to B. Then MP, that is the moment of the ith particle about point P, is R cross MIAI. So this is because M is scalar, so we can bring it out. Then A is this that has been gotten in the part A of our lecture. We have obtained this. So the last term is zero. Is zero. Because here we have R cross R. So that's zero. Because when we open up here, we have R cross AB, then R cross this, then R cross this. So R cross R here give us zero. So expressing the vectors with Cartesian components and carrying out the cross product operations yield this. So MIK, because it's in the Z direction, is equal to MI XI plus J, XI plus YJ, that's for R cross AP in the X direction. Then for this in the Y direction, that's AP, then plus XI plus YJ cross this, that is this cross this. Alpha is in the K direction, then R is in X and Y direction. So we now have this as a final result. So if MI, that is, we now integrate and get the M, and integrating with respect to the entire mass M of the body, we obtain the resultant equation as summation MP, that is the moment about point P, is this plus this plus this, and this is IG, that is the moment of inertia about the center. So here, summation MP represents only the moment of the external forces acting on the body about point P. So the resultant moment of inertia, the resultant moment of the internal forces is 0. Since for the entire body, these forces occur in equal and opposite collinear pairs, and thus the moment of each pair of forces about P cancels out. The integral in the first and the second terms on the right are used to locate the body center with respect to P. This is the first and the second. And then since Ym is equal to integral Ym, and then Xm is equal to integral Xdm, then figure D. Also, the last integral represents the body's moment of inertia about the z-axis. So at least IP is equal to integral R dm. So thus, we have that summation MP, that is summation of all the moments about point P, is minus Ym APX, then plus X bar M APY, then plus the moment of inertia, sorry, the IP alpha. So it is possible to reduce this equation to a simpler form if point P coincides with the mass center of the body. So if that's the case, then X is equal to Y, and then that is X bar is equal to Y bar, which is equal to 0. And therefore, summation mg, that is the mass moment, the moment about the mass center, the summation of all the moments about the mass center is Ig alpha. So this rotational equation of motion states that the sum of the moments of all the external forces about the body mass center is equal to the product of the moment of inertia of the body about an axis passing through the mass center G and the body's angular acceleration. So above equation can also be written in terms of X and Y components of Ag and the body's moment of inertia, Ig. So if point G is located at X bar, Y bar in figure D, then the parallel axis theorem, then by the parallel axis theorem, IP, that is the moment of inertia at point P, is Ig plus X bar square plus Y bar square. When we substitute this equation and rearrange, then we get that the moment of the total moment or summation of all the moments about point P is this Y bar M into APX plus Y bar alpha plus X bar M into APY plus X bar alpha, then plus Ig alpha. So from kinetic diagram of figure D, AP can be expressed in terms of Ag, that is the acceleration of the mass center, as Ag is AP plus alpha R minus omega square R, which is our normal equation that we have derived. So Ag can be decomposed into the X and Y components, and so likewise every other component. So carrying out cross product and equating the respective I and J components, use two scalar equations to equate the I, all the I components and all the J components after carrying out this multiplication, that is cross product. So we have AGX is equal to APX minus Y bar alpha minus X bar omega square. So this is the S component of R. So and AGY is APY plus X bar alpha minus Y bar omega squared. From these two equations, we can see that minus APX plus y bar alpha is equal to minus AGX minus x bar omega squared. And then this is equal to this is equal to this. Therefore, we can have that the summation of moments about point P gives us this plus this is in the x term, the y term, Ig alpha. So the important result indicates that when moments of the external forces shown on the free body diagram are summed about point P, as shown in figure E, they are equivalent to the sum of the kinetic moments of the components of F, that is MAG, about P, plus the kinetic moment of Ig alpha, as shown in figure F, this figure E. So, and this figure F. So when the kinetic moments summation MKP are computed, that is the figure, the vectors, the MAG in the x direction and y direction are treated as sliding vectors. This is, so they can act at any point along their line of action. That is, when you treat a force as a sliding vector, then the line of action, they can act along it. So this MAGX can act on this line, and then MAGY can act on at any point on this line. So in a similar manner, Ig alpha can be treated as a free vector and can therefore act at any point. This Ig alpha. So it is important to keep in mind, however, that MAG and Ig alpha are not the same as a force or couple moment. Instead, they are caused by external effects of forces and couple moments acting on the body. With this in mind, we can therefore write the equation in a more general form. That is, sum of all the moments about P is equal to sum of all the kinetic moments about P. Thank you. This is end of part B. Do not forget to like, to share, to subscribe, to share, and then press notification bell for new videos if you have not done that. And then if you are one of my undergraduate students, please do not forget to subscribe with your real name.